So I ended up in a session with the majority of energy community people. So over here, I will be introducing a product which will allow energy communities to work whatever happens to the voltage of the grid. Okay? So this is a single-phase active voltage regulating system which will allow the voltage of the consumer to be kept at a constant value, so that it will be within the plus or minus 10% allowed by the grid regulations. Okay, the talk will have an introduction. We'll look at what parameters of voltage regulation exist. We'll look then at the topology and how this topology will work. We'll do two case studies actually via simulation, and then some conclusions. So over here you can see the profiles. These are actually of my house. The load profile, the PV profile, and then the combined profile. So over here you can see that when people basically are no longer at home but they are at work, the loads are very low. The PV generates more energy than you've got loads, and you get a reverse power flow. Now in an island like Malta, if everybody is at work and the whole residential area start to generate power into the grid, the voltage along the transmission lines will go up. That is a problem. Also, on the other hand, when people return from work at night, you can see the loads go up. Everybody starts to cook, turn on their computers, televisions, Nintendos, etc. The load goes up, and on the other hand, the voltage goes up. So you need something which actively regulates the voltage which the consumer is seeing. Unfortunately, this cannot be done at the substation because most of substations have got fixed offload. They can change the tap changers, but this has to be offload. So obviously, it's not something which is done, which can be done in real time. So let's have a look a little bit at what we are going to propose. Well, what we're going to propose is a piece of equipment which will allow the consumer voltage always to be within the 50-16-0 regulation, the grid regulation of Europe, which is always plus or minus 10% of the nominal voltage. So the compensator, what we're going to add into our supply is a series compensator. The compensator is going to basically allow the consumer's PV system to continue exporting power to the grid. Why am I saying it will continue exporting power? Because if all the systems generate at the same time and the voltage goes up on the lines, the protection system of the inverter will see an overvoltage and will basically disconnect the inverter from the grid. And like that you lose renewable energy generated into the grid. So it will allow, our circuit is going to allow the PV system to continue to generate into the grid even though the supply voltage is very high. Also, this type of circuit will be able to protect equipment from over and under voltages because it's an active voltage regulator. It's fast enough to correct the voltage, and it will also prevent the tripping of the consumer's over voltage relay, which is something which recently has been introduced into the Maltese electrical grid. Now, one important thing about the topology that we are looking after, just to let you know, this so far is just a simulation study, but we are actually going to build this. We're in the process of building it, in fact, and we'll have a working prototype in about one and a half years. But the criteria were these. We want it to be low cost and reliable. Low cost so that people can actually afford it. Easy to control. We don't want any complicated vector control inside the microcontroller. Okay, we want something very simple, if possibly using just a certain amount of logic, and very efficient. That is, if possible, close to 99% in efficiency. So the idea is this. It's very basic, and it works very well. We've simulated this thing, and basically I'm going to explain to you how these things work. So here you've got your point of coming coupling, that is the main supply. You're going to have your series compensator, which consists of one or two or even more series coils. The one we're going to build, the prototype, will have two coils, compensation coils. with a controller which will switch the coils in and out. The switching of the coils will take place on the low current side. So here you've got your load current. In Malta, the maximum load current can go up to 40 amps. So the site has got to basically be rated at 40 amps. However, over here we'll just have a couple of amps flowing. So that means that we're going to have extremely low losses. Another thing is that we will be using thyristors. Thyristors, you might tell me thyristors, are old technology. No, thyristors are used a lot still nowadays. They are very reliable, they are next to impossible to blow up, and they have got very low loss as well. So we'll basically be using thyristors to do that. And how is the principle of operation going to be? So when we want to increase our voltage, we can increase it at levels of plus 2.5, plus 5, plus 7.5, and plus 10. How is that done? It's done by switching the coils in series. Okay, so we can switch them in series to achieve whatever additional voltage we want to add in this direction. On the other hand, if the PVs are generating a lot of energy into the grid and our point of common coupling, the supply voltage, is very high, then we want to decrease the voltage seen by the consumer. So what we'll do is we will switch the coils in the reverse direction, as shown over here, and like that we can achieve steps from minus 2.5 up to 10%. Okay, so you've got no compensation at all, aiding, that is increasing, or opposing. How will the voltage regulator operate? Basically, a set point will be determined. That will be our 230 volts. And that tolerance band, that is when you are going to ask the controller to switch in. That is variable. The maximum correction that we are targeting towards is plus or minus 10%. Another thing to be said about Malta is that the voltage I showed you, I don't know, no, I didn't show you the voltage profile of my house, but basically in my area the voltage profile is quite steady, so it's not one of the best areas probably where to implement this. However, there are a lot of areas where there's a high concentration of PVs, where the voltage profile basically goes up and down quite regularly. So this profile is going to be very location dependent. If you're in an industrial area, it will be different from that in a villa area or in a rural area. Okay? However, the controller that we are designing shall be able to be implemented in whichever area you require, because it can compensate in the positive direction and it can compensate even in the negative direction. So the first step was for us to simulate our concept. What we did is we had our standard 230 volts 50 Hertz, and we put a distortion source additional to that to get a negative effect of the voltage going above and below the EN 5160 standards. Then, usually when we have got equipment under test, you need to test it using all the rated current conditions. In this case, we did 25, 50, 75, and 100% of rated load. In this case, 40 amps maximum for a Maltese household. So the simulation ran that load. On the other hand, we also tested the circuit whilst having a reverse flow of photovoltaic energy. So in that case, we lowered down the load to around 7 amps, because that is the case when you're going to have PV power flowing back into the grid. And we ramped up the PV, now you see it on the next slide, we ramped up the PV current from 0 up to 16 amps. And we noticed that in both cases, when we've got heavy loads, when we've got reverse power flow, the compensating circuit and the logic behind it worked in such a way that they always managed to keep the voltage within the limitations. So this is our distorted supply voltage, the green one. This red one is the voltage corrected by our series compensator. Okay, over here you can see the load current. So here we're at 25, 50, 75, and 100% of the 40 amps RMS, okay? This is showing you the peak value of the current, not the RMS. So as you can see, the correction is completely load independent. Okay? If we come to the other case study that we performed, it is when we're going to have the photovoltaics generating power back into the grid. So we start with a certain load current, I think it was around 7 amps RMS, and we started ramping up the amount of current produced by the PV. At that point, basically the consumer load is completely being supplied by our PV system. As we continue to increase the PV system, all this here, now this current is being pumped back into the grid. Okay, once again, we assume the grid voltage to be distorted as shown in the green voltage over there, and the controller has managed to a certain extent to control the voltage within the EN 5160 standard. Okay, so in conclusion, over here I have introduced the concept of a circuit that, as I said, will allow consumers to continue to operate as a distributed source of PV generation, so they will continue to operate even though the voltage on the line is not really of very high quality. The circuit is designed to give compensation of up to plus or minus 10% on the voltage with steps of 2.5. We have seen that it works correctly both when we've got load current and when we've got a high load current, and then we've got also an excess of PV generation. We have seen that it's independent of the supply of the current and the direction of the flow of the current. As I said, it will allow your PV system to continue to work without with there being even problems on the voltage. And why did you go for this topology? Why didn't we use an active filter, for example? They're quite well established active filters. The problem with active filters is they are expensive, they are very difficult to control, and unfortunately they are not so efficient. So here we went for a simple control algorithm, very good loss, negligible operational losses, reliable semiconductors, thyristors, and also using this type of circuit. And if you want to increase the plus or minus 10%, all you have got to do is add another series compensation coil. Okay? So, thank you very much. You've got an
Thank you very much. Any questions from the audience? No? Okay, I'll ask something. Well, obviously, the operation from the magnitude point of view of the voltage which is sensed in the system is evident from your simulations. How do you expect, if the system is, let's say, picked up and applied in many locations, how do you expect all the switching of coils to affect, first of all, the power factor of the area, and also the harmonic distortion that will be sensed by the various loads in the system?
This is for domestic. So it will not actually affect the power factor. But what it's going to do is it's not going to help the correction of the voltage on the main grid, because you've still got reverse power flow, which is putting up the voltage, is creating the voltage rises on the lines. So over there, it's not going to help. That should be though the problem of the DLO. They should take care of those things. This will just allow the residential consumer to be able to operate without having problems. And in terms of harmonics, the thyristors, they are not going to be switching all the time, and also they are going to be switching on the low current side. So the harmonics that will be generated are extremely negligible. If you are thinking about harmonics caused by thyristors, you know, you can see the thyristors are on the low voltage side of the coil, so they are going to be extremely nearly non-existent.
Okay. Thank you very much. Any more questions?
So this device will be put on the premises of the user, the final user?
Correct, yes. So it will be on this main distribution board. And in fact, another criteria that we're trying to do is make it as compact as possible. Yeah. Because you don't want to give them a box like that. And you want, you know, so we're even thinking about how to make everything compact, a novel transformer design for this. So there's a lot of practical work now that has to go into it.
Yeah. So because I think that it will introduce also some losses, no?
The losses are negligible because the only losses that you're going to have are over here. And this is the low voltage side, the low current side of the coil. So you have got hardly any losses, and thyristors, once they are on, the voltage drop is very small, about 0.3, 0.5. So the losses, we're expecting it to be about 99.5% efficient, this equipment.
Okay.
Okay, thank you very much again.